Okay, so let's have a look at what we've learned about probability in terms of and apply it to a couple of questions. I think these ones look like they're going to be fairly straightforward. Mark an X on a probability scale, the likelihood of each event. Well, heads, half, winning the lottery. Okay, well, I guess it's like demonstrating that you know that it's very unlikely, so somewhere around about here, but not actually on zero. Sun comes up tomorrow. Well, somewhere up about here, not necessarily one, I suppose. Roll a zero on a fair standard dice. Dice don't exist, don't have a zero on it, so it's going to be zero there. So fairly straightforward. Let's look at the end. Ben flips an unbiased coin 3 times, so each time is going to be heads. He states that it's more likely to get heads, tails, then all tails for the 3 flips. So let's have a look. It's more likely to get heads, tails, then tails for all the 3 flips. Is he correct? No, because he's describing a specific outcome, although the outcome that he's describing looks fairly random. It's not random because he's described it. So it's head, tails, heads. The likelihood of getting a head is half. The likelihood of getting a tails is half. Likely of getting heads again is half. So it's going to be half times half times half, which is going to be an eighth. And that's the same as if it was all 3 tails, an eighth. So there's some examples there. Let's have a look at this. 3 friends flip the same biased coin several times. Oh, it's a biased coin. Okay. So in other words, you're more likely to get either a head or a tail than the other. Each of the friend calculates their own probability of heads. Which friend is likely to have the probability closest to the true probability? Well, what you have to understand from this is that the more times you repeat an experiment, the closer to the actual answer is that you're going to get. So for example, if I flip a coin 3 times and I get head, tails, heads, then I might decide that the chance of me getting a head is 2/3. Well, clearly that's wrong. Whereas if I did it a million times, then it's going to get much more closely approximate to 50-50. So the more repeats you get, the more reliable it's going to be. So the person with the highest accuracy, or highest, closer to the true probability, is going to be Sonia. And yeah, so I just explained the answer. And if it asked you to work out what her probability would be, you would add up these two. That's a total number of coin tosses. Then do 33 divided by that, and that will give you the probability of getting heads. So clearly, it's much more likely to get tails than heads with this biased coin. Let's see if we can find some more questions then. This time we'll do some probability tree questions. Okay, so this can be found in my database as well now, by the way. So right click here, copy link address. Let's have a look at some probability trees. It looks like it's quite cool in this website, by the way. If you've got a QR scanner, then you can scan that and it shows a video of how to answer these questions, which is quite useful. All right, so we want to go all, extract, and let's get the answers as well. Copy link address. Oh, big one this time. Maybe okay, so I've got the answers and the questions just down there. Let's have a look. We had a look at this in the previous video. Let's see if we can answer them now. So, in fact, I've done this question before. So he has, so James goes to an arcade. He has a go on the teddy grabber. So probability that he wins the teddy grabber is 0.2, which means this one is going to be 0.8, isn't it? Okay, and so basically, there's only 2 options. So the 2 probabilities must add up to 1 because it's either going to do that or that. That's what the diagram is saying. So this one here is going to be 0.7. And if we read it carefully, then yeah, that's going to be 0.3 and then 0.7 again. Okay, so that's completing the diagram. Work out a probability that James wins on the teddy grabber, and he also wins on the penny drop. So remember what and look at the word and. He's going to do this, and he's going to do that. What's the probability of both of them happening? You're going to multiply them together, so it's going to be 0.2 multiplied by 0.3. Okay. Now this is a straightforward condition probability tree where the probability of the second event is not impacted by the first event. So what we want to do is look at one that is impacted. Now, actually, I think this one is the same straightforward one, but we're going to edit it. Natalie has 8 socks in a drawer, so 5 are black, 3 are white. So probability of getting a black sock is clearly going to be 5 out of 8, 3 out of 8 for a white sock. Now look what it says. Natalie takes out a sock at random, writes down its colour and puts it back in the drawer. If she didn't put it back in the drawer, what would it look like? So first of all, we'll fill it out as if she did put it back in the drawer. So it's going to be 5/8 and 3/8, and then it's going to be 5/8 and 3/8, and we're going to copy those. In fact, oops, and let's lock that. I'm going to copy those down like that. Could have copied the first one as well. Anyway, this would be if you put it back in the drawer. Now, how would this change if you didn't put it back in the drawer? Well, this would not be, there wouldn't be 5 socks anymore. There'd be 4 socks and 4 black socks, and there would be a total of 7 socks, not 8. So what's the probability of getting a white? There's still 3 socks, but you're pulling it out of 7 socks, aren't you? Okay. Whereas in this case, again, you've taken out a sock, so these totals are still going to be 7. But the difference being is that the black stays the same now because you haven't taken. There's still 5 blacks in there, and the whites will go down. So we've taken out one of the white socks, so we're now 2 white socks. So this is a situation, an example of how you could do a probability tree where it does get impacted. All right, I'm going to rule all that out. So as you can have a go at it yourself. Let's have a look at this one now. Probability. A football team has 2 matches to play. The probability of the team wins is 0.6. The probability that they draw is 0.3. So the remaining probability is going to be 0.1. The chance of them losing is 0.1. To fill it out again, it's just going to be the same because the second match doesn't seem to be dependent on the first match. Okay, so maybe you could imagine how this could be edited and say maybe if the team loses the first match, maybe the probability of them losing the second match might increase because their morale is down, or maybe the probability of them winning might increase because they're going to try a lot harder this time around. In any case, you can imagine how that could be edited, and the second probability would depend on the first. That's touching upon the topic of conditional probability. So probability is conditional on something else. I'll just briefly dip into conditional probability now then, I suppose, while we brought it up. Let's imagine a much more simple situation of conditional probability. What's the probability of me getting 2 heads? This is not conditional. Well, the probability is going to be 0.5 times 0.5, so 0.25. Probability of me getting 2 heads, given the condition I've already got 1 head, well, clearly that 1 head is already happened, so that's a guaranteed, and so it's going to be time. Well, so you can say, I suppose, one way to think about it is you could say the probability of me getting a head once, if I've already got a head once, is 1. So the probability, because it's happened, right? Probability of me getting a second head is 0.5. So you could say it's 1 times 0.5, which is 0.5, of course. What's the probability of me giving two heads, considering it, given the condition I've already got 1 head, 0.5. It's worthwhile touching upon this. One of the interesting things about probability in maths is it actually is related to psychology in a weird way, because if you hear this all the time, and most people nowadays don't fall for it as much, but let's say that I flipped a coin and I've got one head, so 3 heads. And in fact, let's say that I've got 6 heads now in a row. What's the probability of me getting a 7th head? It's still 50%. It doesn't matter. It doesn't matter about what's happened before. The probability of me getting another head is 50%. So we sort of think it's basically a misunderstanding of probability, isn't it? If the events have already taken place, it's not going to. Then we don't. Well, it's happened. So yeah. So that's a brief introduction to conditional probability. However, in some cases, previous events do affect future events. Like example I said before, that maybe a football team tends to is more likely to lose a match if they've just lost a match, or maybe more likely to win a match if they've just lost a match, and so on. So that's a brief introduction to probability trees. Let's maybe just jump to the final question and see how we get on with that. Jennifer is playing darts. She throws 2 darts, aiming for a bullseye. Probability of she hits the bullseye on her first throw is a quarter. Probability she hits a bullseye on her second throw is 1/3. Okay, yeah. So this is kind of it's not really quite conditional because this probability does not depend on the outcome of the first event. It doesn't say if, right? So I guess the key word, if we're going to be talking about if conditional, it's conditioned on a particular incident, on a particular event. So we want to use the word, we're looking out for the word if in that. This is not conditional on anything. The probability of her getting hits the bullseye on a second throw. Just look at the wording. Let's read the wording just to be sure. It doesn't say given that that she's got a bullseye on the first throw or anything like that. So it's just simply for some reason her second throw is always worse than her first. Better than her first. I suppose that does make sense because you just correct for. Yeah, that does make sense actually. Okay, so 3/4, 2/3, 2/3. Okay, now we've got an or situation. Work out a probability of hits the bullseye at least once. Well, that would be these. You can imagine that's one route, that's 2 routes, that's a 3rd route, that's a 4th route or combination. Hit the bullseye at least once. Well, that would be. It could be a hit, could be a hit-miss, could be a miss-hit, but it can't be a miss-miss. These are so it's basically this, or this, but not that. Okay, so we go. It's going to be 1/4. This combination is 1/4 times 1/3. This combination is 1/4 times 2/3. This combination is 3/4 times 1/3. And you're gonna work out the sum, the answers to these ones, and then because that's going to be that and that, that and that, that and that. But we're saying any of these situations could happen. So then it's going to be this or this or this. So that's when you do add. So remember, or is add, then and is times. Okay. So I shall delete all that as well, so you can have a go at it without seeing my answers, and you can rewatch the video. You can watch the videos to see how I did it. Okay, hope that's useful. Cheers.